Hello and welcome. We, Claudio Gomes, and yours truly, Wilshawn Alexander, would like to present our final project. In this video, we will talk about the implementation of our round-robin scheduling program and discuss the results from how changing variable values, time quantum and context switch time in particular, can affect the execution of task scheduling. We have broken this video into parts. We will start with the code showcase, where we go under the hood and see how our simulation works, followed by the program showcase, where we go to the terminal and execute our program in a user perspective. Lastly, we will analyze our results from the data that we have produced using our program. So let's get started. Welcome to the Code Showcase. I will show you how some of the main program works, including the concepts implemented and how things are calculated. So first, looking in the main function, you will see many of the variables that we use being initialized here. We will talk about those more in depth as we go through the code. The next thing I want to talk about is this ifstream function here. This allows you to read the file where the process data resides in. If the file can't be read due to it not being found or other reasons, then it will give you an error code. Let's switch over to the process text file. You will see data already supplied to us. A process is represented on each line. Each one will have a arrival time followed by a service time. The code will then read the file and save each process in its initial properties in an array of process structs. We will talk about this structure more in a moment. The process arrival and service time is then converted into milliseconds, and the last three properties are used to track the processes while in the simulation. This iteration will continue until we have stored all the processes. This is determined by our const variable size, which is defined as 22. Let's go back up towards the top. This is how our processes are stored. We define these as a struct. That way we can add properties we need with any type of data type. The process structs will store the arrival time, service time, status, remaining service time, turnaround time, wait time, and a Boolean that lets you know if the process has initially ran or not yet. We have defined an array of process structs right here. After the processes are defined, the program would then ask for the dispatcher overhead time, context switch time, followed by the time quantum. Now, after the user inputs both, they both will be stored as a variable moving forward. This will also throw an error if the inputs are not positive ints. Now let's talk about the simulation. We now start a while loop that we will continue until all processes are completed. We keep track of all the processes completed in a variable and compare that to the const size variable. We also assign the start of the loop time variable to the current time when this iteration is first started. This allows us to check if we need to continue and progress the time if there is no activity by the end of the iteration. So in this while loop, we have a for loop that we loop through each process. For each process, we will run conditionals to determine if we need to modify properties and update calculations. First, we will skip the process if the process has already been completed or if it has not arrived in the queue yet. If the process has arrived and is ready, we will make a log of this and add it to the ready queue. When it's time for the new time quantum to run for a process, we check if its remaining service time is less than the full quantum time for the programmer or not. If it's bigger, the process will run its routine time quantum and go back to the ready status after completion. We will also update the remaining service time and current time of the program. If the time quantum is actually less than the remaining service time, then that means the process is about to be completed fully. We will run the remaining service time, modify the current time accordingly, and make a note that this process has completed. We will also calculate the current process wait time if it's about to run for the very first time with the initial run completion variable and by updating the wait time property. Throughout the loop, we log process milestones like when it initially runs, when it completes, or when it changes its process state. Once all the processes have been executed, the while loop in the simulation ends. Once the while loop ends, we finalize the calculations for the total simulation time, average ready queue length, average turnaround time, and the average wait time. And then voila, we now output all of our beautiful data that we have collected. So now let's actually take a look at this code in action on the command line. All right, welcome. You've seen the code, so now let's see the program in action in this showcase. So I have already navigated to where my code is located. I will now compile it and use my out file to run it. When the program starts, it will ask for a dispatcher overhead time. Keep in mind that it has to be a positive int or 0 for it to be accepted. I will put in 5. So then it will let you know what you inputted, followed by asking you what you would like the time quantum to be. The input has to be a positive int. I will make the time quantum 100 here. So now you will instantly see the results. If we scroll up a bit, you will see the program output any process milestones, like if it was running, when it completed its task, etc. Going back to the bottom, we see a data key, individual results for the process, including the service time, wait time, and turnaround time. Next, you'll see even more data. The data provided includes the user-given time quantum and context switch time, the calculated total simulation time, average turnaround time, average process wait time, average queue length, and maximum queue length. So there you have it. In the next section, we will talk more about our results and how context switch time and time quantum length affects CPU scheduling.
Hi there, my name is Lailson Gomes and welcome to our breakdown of the results from our study on round-robin scheduling. Over the few minutes, we will explore how time quantum and context switch time affect key performance metrics like turnaround time, queue lengths, wait times, and simulation time. Stick around because we're going to make this fun and easy to understand. First up, here is figure 1, giving us a bird's eye view of all the results we collected during the simulations. Now, in round-robin scheduling, time quantum decides how long a process gets on the CPU before it's interrupted, while context switch time refers to the time needed to switch from one process to another. By testing different combinations of these parameters, we were able to uncover some pretty exciting insights about system performance. The key takeaway here is simple. As we adjust the values for time quantum and context switch time, the metrics like turnaround time, simulation time, and queue length are directly affected. Let's dig deeper into each of these results, starting with turnaround time. Now onto figure 2, this one's all about average turnaround time, basically the average of time process completed execution minus process arrive time. When the time quantum is small, like 50 milliseconds, the average turnaround time is much higher. Why? Because processes keep getting preempted before they finish. It's like being in a line at the coffee shop and the barista keeps taking breaks before finishing your latte. But what happens when we increase the time quantum, say, to 50 or 500 milliseconds? the average turnaround time drops significantly because the processes are interrupted less often, letting them run longer before having to return to the queue. You'll notice that the improvement levels off as the time quantum increases. Figure 3 is all about how crowded the rarity queue gets. This is the average rarity queue length. Smaller time quantum values mean more processes waiting in line, like a traffic jam. Every time a process gets preempted, it's sent back to the queue, which makes the line longer. But as we increase the time quantum, the queue starts to shrink because processes get enough time to finish without being interrupted. Context switch time plays a role here too. Higher context switch times at smaller time quanta make congestion worse. But once the time quantum is large enough, things smooth out. Now let's move on to figure 4, which focuses on the maximum ready queue length. This is the longest the queue ever gets during the simulation. The trends here are not very consistent with what we saw in the average ready queue length because it highlights extreme events during the simulation. Smaller time quantum values tend to result in dramatically long queues because of those constant interruptions, especially when context switch time is high. But increasing the time quantum helps stabilize the maximum queue length since processes have more time to run before being interrupted. Alright, now let's talk about figure 5, which deals with average wait time. This is the average time that each process spends waiting in the queue before getting CPU time, or average of first time process begins execute minus process arrive time. You'd think that smaller time quantum values would result in more waiting, but it's actually the opposite. For smaller time quantum sizes, processors are more frequently allocated CPU time. However, there is a catch. As context switch time increases, the average wait time grows significantly, with a minor asynchronous behavior over the variation in time quantum. This graph shows the total simulation time, how long the system takes to process all tasks. Smaller time quanta increase simulation time due to frequent interruptions and context switch overhead, especially when switch time is high. Larger time quanta reduce these interruptions, letting the CPU work more efficiently. Now, the conclusion. So, what did we learn from all this? The key takeaway is balance. Smaller time quanta can be more responsive, but come with overhead from frequent context switches. Larger time quanta reduce that overhead, but also increase wait times. The most efficient scenario we found, a time quanta of 500 milliseconds with no context switch time. These simulations are super useful for understanding how to configure round-robin scheduling to get the best of both worlds, responsiveness and efficiency. Thanks for watching, and I hope this breakdown made it all clear and a little fun. See you next time.